Hello viewers, in this program of the series of public health engineering, we shall see as how do we measure conductivity of water. Conductivity of water or a solution is the property by virtue of which the current is passed through it. The ions in the dissolved form present in the solution act as carrier of electrons. Thus, more the number of ions dissolved, more will be the value of conductivity. Conductivity is measured in terms of micromoles per centimeters, or a bigger unit is millimoles per centimeter. Another unit of measurement is millisiemens per meter. The instrument used to measure conductivity is called conductivity meter. It is a simple instrument based on principle of potentiometry. We also need to have a conductivity cell and a temperature measuring device. The conductivity meter has three controls: a function switch which can put the instrument in a calibration or measurement mode. The cal position is used when we are calibrating the instrument, mhos when the measurements are being carried for conductivity, and ohms if we need to measure resistivity of the solution. The cell constant knob is used for synchronizing these conductivity cell with the instrument. This third switch called range switch, which is used to select appropriate range of conductivity depending on the expected value of conductivity in the sample. Now, to begin with, we will switch on the instrument and allow it to warm up for some time. Connect the conductivity cell to the instrument. Now read the value of a cell constant which is specified by the manufacturer. For this cell, the cell constant value is 0.96. So, put the instrument in calibration mode and adjust the value such that the value equal to cell constant is displayed on the instrument. It is advisable to check the accuracy of the instrument at suitable intervals. This is done by measuring the conductivity of a standard solution of known concentration. Prepare standard solution by dissolving 0.5232 gram of potassium chloride dried for 1 hour in 1 liter of deionized water. This solution has conductivity of 1000 microsiemens per centimeter or 1 millimole per centimeter at 25 degrees centigrade. Alternatively, dissolve 0.7456 gram of anhydrous potassium chloride dried for 1 hour in 1 liter of deionized water. This solution has conductivity of 1408 microsiemens per centimeter or 1.408 millimole per centimeter. So, we take the standard KCl solution of concentration 1 millimole per centimeter. On measuring its conductivity, the displayed value is 1.003 millimoles per centimeter. This is very close to the value 1. So, therefore, we can say that the instrument is calibrated rightly. Now, in case of any discrepancy, the conductivity cell would require platinization. This is done by following a specific procedure in which the cell is washed with chromic acid first and then placed in platinizing solution for certain period of time. So, now the instrument is calibrated and the cell is in synchronization with the instrument. Now, we can make the measurement because the instrument is ready for use. To measure the conductivity of a sample, we will take the sample and simply dip the cell in it, put the instrument in Mohs, so the meter is displaying 0.331. So, this indicates that the reading is in low range. So, to get better accuracy, we will put the instrument accordingly. When the reading is stable, we will note down the value. So, conductivity of this sample is 0.290 millimoles per centimeter or 290 micromoles per centimeter. The conductivity of a sample is also dependent on temperature. With the increase in temperature, the activity of ions will increase and so will the conductivity value. So, therefore, the standard temperature of measurement, which is 25 degrees centigrade, should be used for measurement. If we are not making the measurements on 25 degrees centigrade, then we need to apply a correction. So, measure the temperature of the sample. The temperature of the sample is 22.5 degrees centigrade. Now, corresponding to this temperature, we can find a correction factor from the table. The correction factor is 1.05. To determine the corrected value, multiply the observed value by the cell constant and this correction factor. So, in this case, the corrected value is 292.3 micromoles per centimeters. Since conductivity in water is due to ions present which are because of the dissolved solids. Therefore, the conductivity values can be taken as the indicators of total dissolved solids. To find out total dissolved solids, multiply the conductivity values in micromoles per centimeter by a factor 0.55 to 0.9 to get total dissolved solids in mg per liter. For this sample, the corrected conductivity is 292.3 micromoles per centimeter. To get total dissolved solids, we multiply this value by an average factor, say 0.75, and get the value of total dissolved solids in mg per liter. Now, based on the same principle, some of the instruments are pre-calibrated to read total dissolved solids value directly. Now, such instruments use a single conversion factor. However, it would be more precise to specify a range of total dissolved solids based on conductivity values, because different ions present in the water contribute differentially to the development of conductivity. Thank you.